Hello everyone, today we're going to talk about linear, time invariant, and invertible signals. In signaling systems, a signal is linear if we apply the input AX1, so we create X1 and X2 and let them be two different inputs, okay? And then we have coefficients A and B that are not equal to 0, and we pass them through the system in this manner. And if it is equal to A times the system individually applied to X1 plus B individually applied, or X2 individually applied to the system times B, then the system is linear. Now for time invariant signal, it could be sometimes confusing, but it's pretty easy. The first step is we shift the output signal by t minus t0. So this is literally replacing everything you see with a t by t minus t0, pure substitution. And the second step is to take the input x of t minus t0 and then pass this through the system, or h. And then you get an output, y of t. If this y of t is equal to this one, then the system is time invariant. And lastly, for invertible, you need to find a system, so let's say Wt, such that whenever you pass Wt, W of x of t, you get x of t back. Alright? And you need to also have one-to-one mapping for this. So we'll talk about we'll do some practice problems and some examples of each of these properties. Okay, so for part A, let's find a h1 x of t. So this is going to be equal to, let's first do h1 x of t, and what do we get? We get x1 of at minus b. Then we have to multiply by a, and we get ax1 at minus b. Same thing for x2, so we do, this should be x1 here. So x2 of t, and we're going to get x2 at minus b, and b x2 of at minus b. Okay, by the way, a and b here, like, could be different constants. It could be like c and d here, for example. Okay, could just use c and d because we already have a and b, so let's just use c and d. Okay, so we get this, and now we have to pass into the system h of c x1t plus d x2t. Okay, what do we get? We're gonna get c x1 t, c x1 of at minus b plus d of x2 at minus b. If we take the sum of these two, okay, if you take the sum, you're gonna get an equation, call it equation 1, and it's gonna be equal to this equation, equation 2. So because equation 1 and equation 2 are equal, the system is linear. Okay, let's solve for part B now. Similar problem. Part B, we have to do the same thing. So we say a x1t, we're going to pass it into the system. Well, first, just pass x1t into the system. What do you get? You get the integral of from t minus 1 to t plus 1 of x1t. And it's going to give you x1 tau d tau. Now you multiply by a, and you get a integral t minus 1 to t plus 1 x1 of tau d tau. Do the same thing for x2, and you're going to get, the same thing. So integral from t minus 1, t plus 1, x2 tau d tau, and then this is going to give you b t minus 1 to t plus 1 x2 of tau d tau. And the sum of these two is going to be our equation 1. Okay? Now, what you need to do after is let the system have ax1t plus bx2 of t. Now think of what the system is doing. It's taking the integral from t minus 1 to t plus 1, and it doesn't do any changes to the signal itself. So this is going to give integral from t minus 1 to t plus 1 of ax1 tau plus bx2 tau d tau. And from the rules of integration, we know that this could be decomposed into a integral from t minus 1 to t plus 1 of x1 tau d tau plus b integral from t minus 1 to t plus 1 x2 of tau d tau. And now this is our equation 2, and because equation 1 equals equation 2, it's linear. Alright, let's do one more problem, and then we're going to move on to time invariance and time variance. Okay, so for part C, we have to determine if the system is linear. Same steps. x1 goes through the system, we get x1 squared t. x2 goes through the system, we have x2 squared of t. Okay, and then we multiply by a on the first one. What do we get? ax1 squared of t. And then here we get bx2 squared of t. Take the summation. What do we get? ax1 squared plus bx2 squared of t. Okay. And now we pass through the system the input with ax1 t plus bx2 t. What do we get? This is actually gonna, we see that the system, what does it do? It squares the input. So we're gonna get ax1 t plus bx2 t squared. And this gives us, it gives us a squared x1 squared t plus b squared x2 squared t plus 2 ax1 or 2 ab x1 x2 t. So we could see that equation 1 and equation 2 are not the same. Oops. So the system is not linear. So we decided equation 1 does not equal equation 2. Oh my god. Therefore, non-linear. Alright guys, that's it for linearity. So now we're going to move on to time variant, time invariant problems. Okay, here's the first problem. So try to do it yourself. I'm going to write the solution. The first step is we always take the output. So let's write that this is y of t. Okay, let's consider this as y of t. Now y of t is equal to 3x of t minus 1. The first step is we write y of t minus t0. So we shift the output. Okay, this is going to be equal to 3x of t minus t0 minus 1. This is a direct substitution of t by t minus t0. Okay, here we have a shifted output. Now we're going to shift the input. So we're going to pass into the input x of t minus t0. Alright, so what does this give us? The function we can see just multiplies the function by 3, so 3x, and then it takes whatever the input was, so t minus t0, and then does minus 1. So this function is the shifted input. And because the shifted input is equal to the shifted output, this system is time invariant because it doesn't change. Now let's do. So at this point, this is what you need to do. Just let h of x of t be y of t, and now we're going to write y of t minus t0, and this is going to be the shifted output. It's going to be a complete substitution. Every t that we see, we replace by t minus t0. So with this minus, and then here t minus t0, everything divided by 2. This is the shifted output, sorry. Now this is going to be equal to this, but this second term is going to be equal to t0 minus t. Shifted output. Now we're going to pass the system, we're going to pass the input x of t minus t0, a shifted input, into the system. This is going to give us x of t minus t0 plus x of negative, so this does not change, and then we pass whatever value was in the input, so t minus t0. Then we divide by 2. So this is our equation 2, our equation 1 here, and we can see that equation 1 does not equal equation 2. So the system is time variant, or you could say not time invariant. For the last problem on time variance, I want to mention that this specific question was asked on my midterm exam in 2026, winter 2026. So we're going to solve it together and pay close attention. We do the same steps. So the first one, we shift the output, and what do we get? Well, we get t minus t0 because we substitute t by t minus t0, and then we have minus 1. And here we have sine of x of t minus t0. Okay, very simple first step. The second step is to shift the input and pass it through the system. So what this means is we shift the input, okay? Now we're going to pass it into our system. What does our system do? It multiplies, first of all, by t minus 1. So we keep the t minus 1. Right? This has nothing to do with our input. We only shifted our input, so it's only going to affect whatever's inside our inputs. So x of t, and we shifted by t0. That's it. So we could see that equation 1 and equation 2 are not equal to each other. So the system is time variant. A quick giveaway I can give, like a little tip, is you can tell if a system is time variant or not by looking at what operations were done. If you have something like this, a x of t or a x of t minus h, okay, you can have any coefficient, constant coefficient here, and you can have any shift, and it will always be time invariant. All right, you should always prove it to double check, but if it's constants that are in a and h, then it should always be time invariant. Okay, but if you have any other operations, it could still be time invariant, but you do have to double check. You have to write out the whole proof. So yeah, this problem was given in my exam, and it might be something similar in your exam. So I strongly recommend you keep doing problems on time variance until you really understand it and understand how to do it. Sometimes it's not evident, but I hope I did my best to try and show how it's done. Okay, so here, for this last set of problems, we have to determine if the system is invertible. So how do we do that? Well, invertibility, it doesn't have like one way of finding the solution. What we have to do is kind of like take an educated guess on how we can reverse the system, all while maintaining one-to-one mapping. So what does this mean? So for example, part A. here we could see that we multiply by t by a, and then we shift by b. So how could we reverse that? Well, we have to pass through here, through the system, an input that will reverse x of at minus b. So I would guess 1 over a to remove the a, and then t plus b. So let's see what this would give us. If we put this into the system, we would get x of a, right? And then times t. But now our input is 1 over a times t plus b. And then we have minus b. Now what's going to happen is this a is going to cancel here, but here we're going to have ba minus b. So we can't have that. So actually, maybe I should do 1 over a here, and then times t plus b, because the scaling applies to the shift. So you could see we talked a bit about that in one of my first videos on function transformation. So now in this case, we actually have t plus b in here, in another parentheses. Now a is going to cancel 1 over a, and then we have t plus b minus b, which is just equal to x of t. So there you go. We put an input into the transformation system, or the transformation function, and we got our input back. We got x of t. So we could say that g of t is equal to 1 over a t plus b. Okay, you just let g of t equal this, and now we could say the system is invertible, and usually they ask this, the inverse function is g of t. Okay, so there you go. The system is invertible, you proved it, and the inverse function is g of t. Now part B. Is the system invertible? So what can we plug into y of t, or into the system, to get x of t back from e to the x of t? Well, if we take ln on both sides, we know we're going to have ln y of t equals x of t. So there you go. This is the inverse function. You could tell because if you plug in into the system ln of y of t, what do we get? You get e to the ln x of t. Sorry, it should be x of t here. Okay, now this gives us x of t. There we go. So the system is invertible, and what was it? Ln y of t is the inverse function. And y of t is what? Y of t is equal to the system transformation of x of t. Okay? Okay, so for part C, it might look a bit easy, but actually we have to be careful because of the one-to-one property. So in this case, you would be like, okay, how can I get x of t? You just take the square root of y of t, right? And then you get plus or minus y of t is equal to x of t. The issue with this is that we have 2-to-1 mapping. For example, if let's say x1 t is equal to a, and x2 of t is equal to negative a, right? And we pass it into the system. So what are we gonna get? We're gonna get here a squared, because it's gonna be it's just gonna be a squared, and then here we're gonna have negative a squared by the system, right? Which is also equal to a squared. Now the issue with this is the problem is that we cannot invert the system, because the whole point of invertibility is that if I give you the output a squared and I asked you what was the input that gave me a squared, what was the input? You can't tell me exactly which one it was because it could have been a or it could have been negative a. So we have 2-to-1 mapping in this case, and that's why it doesn't work. Another case where you should be careful of this 1-to-1 property is with absolute value, right? The negative becomes positive, so again 2-to-1 mapping. So always be careful with these kinds of cases and make sure that the 1-to-1 property holds. But other than that, that's it for this video. I hope you guys enjoyed. If you need help with any specific question or any problem, send me an email. Here, I'm going to pop it up on the screen. And have a good day.